Okay, so what we're going to look at today is electric current. So the first thing to think about is what does it mean to actually have a current? So we're more familiar with rivers, perhaps. So if you take a look at the Mississippi, which if you've gone to St. Louis, you've crossed, or anywhere out west, the Mississippi River is a fairly slow-moving river. Its velocity is somewhere around 0.3 meters per second. It's not very fast. On the other hand, if you've been to Pigeon Forge or Gatlinburg, you may have gone rafting on the Pigeon River, which is a river which moves very fast. Its velocity is about 3 meters per second. So the question is, if the Mississippi River moves at 0.3 meters per second and the Pigeon River moves at 3 meters per second, which one has a greater current? And it's tempting to think that the one that moves faster has a greater current, but that's not really true. So current is not about how fast the water is going. It's about how much water passes a given point in a given amount of time. So for the Mississippi River, there's about 600,000 cubic feet of water that goes by every second. So every second, 600,000 cubic feet of water passes by a point or is dumped into Lake Pontchartrain at its terminus down in New Orleans. On the other hand, the Pigeon River only has about 1,000 cubic feet of water per second. So although it's moving faster, there's not nearly as much flow. And so current is the volume divided by the time, right? So current is defined as the rate that a given amount of something, in the case of the river, it's water, passes a point in a given amount of time, usually in a second. So for river volume, it's the volume of water per second. And for electricity, electrical current, we're not going to measure the volume of water. We're going to measure the amount of charge that flows through a conductor in a given amount of time. So when we talk about electrical current, we're talking about how much charge flows in a given amount of time. So electrical current is the charge that flows through a conductor in a given amount of time. And we're going to measure this in a unit called an ampere. So it's usually abbreviated as amps. But 1 amp is what you get when 1 coulomb of charge flows by a point in 1 second. So an amp is a coulomb per second. A coulomb of charge going by in 1 second is 1 ampere. So 20 amps is 20 coulombs of charge in a second. So symbolically, we can represent this relationship as follows. The current, I, and we use capital I for the current. Mathematicians will scream at that because I is a reserved variable, but it's what electrical engineers use, and so it's what we're stuck with. So I is the current, and it equals the charge that flows divided by the time. So we are imagining some surface here, this imaginary surface. We call it the cross-sectional area, and if you count how many charges go by in 1 second, the charge divided by the time is the current. Okay, and the standard units we're going to use, time is in seconds, charge is in coulombs, and amperes is in coulombs per second, which is why we have to use amps. Okay. Thanks to Ben Franklin, we're a little bit screwed up on the direction. So the conventional current is the current that Ben Franklin postulated. And if you imagine a battery or a positive terminal, positive charges would flow out of here, would go around the circuit, and would go back in the other side. And so we would say the red arrows represent the flow of positive charges, which is what we call the conventional current. The only problem is we now know that positive charges don't flow. So it's actually the electrons leaving the negative terminal, which move around the circuit in this direction, and we call that the electron current. So the conventional current, or just the current, is the direction positive charges would flow if positive charges flowed. But they don't. So the actual electron current is in the opposite direction. The electrons go from the negative terminal around to the positive terminal. Okay, so there's a little bit of confusion there, mismatch. After a while you get used to it. It's a pain, but unfortunately we're stuck with it. Okay, so that's our current direction. We have defined our current to be the ratio of charge to time. And so now we can solve some simple problems. If you've got a hairdryer in the morning and 1,000 coulombs of charge flow by a point. So if you imagine you make a little mark on your cord and you measure how much current flows by, 1,000 coulombs go by during 1 minute. What would be the current? So what we're looking for is the current, I. The charge is 1,000 coulombs. And since current is coulombs per second, we need the time in seconds, so I convert the time to seconds. And then we can calculate the current, Q over T, which is 16.7 amperes. So your household circuits are generally 20 amp circuits, which means 20 amps of current is allowed to flow. If you try to use more than 20 amps of current, the circuit breaker will trip. So if you and your sister both tried to use a hairdryer at the same time, you might trip the circuit and it would shut off and you have to go reset it. So 20 amps is the limit, and a hairdryer is pretty close to it. So this is 16.7 amps or amperes. 16.7 coulombs every second, which results in 1,000 coulombs over 60 seconds. Okay, another example, think about your iPhone charger. What you do when you plug it in is you allow current to flow, and that current charges the battery on your phone. A typical iPhone charger delivers about 1.25 amps or 1.25 coulombs of charge every second at 5 volts, and we'll use this in a little bit here. So if you are sending 2.4 coulombs of charge every second, there's a mistake there. That should be 1.25 coulombs of charge every second. So if it takes a full hour to charge your battery, how much charge was transferred to your phone? So what we're looking for, we got a current of 1.25 amps, so here's the current. The time is 1 hour. Since amps is coulombs per second, we need the time in seconds, and we're trying to find Q. So we are going to use this equation, I is Q over T, to find Q, the charge that is transferred to your phone over the course of the hour that you're charging it. So solving this for Q, you get Q equals I times T. Multiply them, you get 4,500 coulombs. So during the hour you charged at 1.25 amps, you added 4,500 coulombs of charge to your phone battery. Okay? Now, how much energy does that represent? Well, you may remember from yesterday that the voltage is the energy divided by the charge. We know the charge, we just found it. It's 4,500 coulombs. We know the voltage, your phone operates at 5 volts. That's the voltage that USB chargers use. And we could solve this equation down here for potential energy. So if we know the voltage is 5, we know the charge is 4,500, we're going to solve for potential energy. So the potential energy will be the voltage times the charge. That's 5 volts times 4,500 coulombs. Remember, a volt is a joule per coulomb. Multiply that by 4,500 coulombs, you get joules. So you get 22,500 joules or 22.5 kilojoules. So that's the amount of energy you added to your phone when you charged it for an hour. And so that's how much energy your phone has to use over the course of the next however long you're going to have it before you plug it back in. So in summary, the the current measured in amperes tells you the rate that charge is flowing. It's the charge divided by the time. And we can use that to figure out how much charge we need or how long it will take to charge something. Okay, so now you're going to hop online and go to some problems where you're going to practice yourself solving these.